Hello, everybody. So marching on, we're going to take a look at another technique for integration. We're not going to get too bogged down into justifying this. It's essentially using the substitution rule in the opposite direction. And so we mostly right now just want to focus on learning how to perform this. So let's start with the following. So let's just think about, I'm going to draw a little graph here of the unit circle, right? That's the circle with a radius of 1, and let's have it centered at the origin. And let's just look at the top half of this circle, right? So something like, oops, I did not mean to do that. So we're just going to look at the top half of the unit circle. There we go. There we go. Okay, sorry about that. So let's sketch this. It's going to be something like that. Okay. So again, centered at the origin with a radius of 1. Okay. Now we know the area of this circle, right? We know the area of a circle is pi r squared. So the area is just going to be half of 1 squared, or pi over 2. Okay, but let's see if we can get at this area from another direction. Undoubtedly, what I'm about to do is way more complicated than that formula that we have there. We know this formula already. That's not the point of what's coming next. We're going to be using this technique on other things. So let's start with a simple example. Okay, so the unit circle has the equation x squared plus y squared equals 1, and we can solve this for y, and this is actually the top half of the unit circle, so exactly what we are looking at here, right? Solving for y actually gives us 2 solutions, the plus and the minus, the positive and negative of this radical. So we just want the positive one. So this here then is a function. This is the graph of this function, right? And this, of course, goes from -1, 0. That's the corner there, or the intersection there, and the intersection there. So if everything we've been talking about in these videos is correct, the area under this curve, right, which of course is the area we just found, can be given by this integral. Right? But this is not an easy integral to take, okay? Like I said, we can do it with this formula, but things of this form, right? Radicals with combinations of our powers of our variable show up in lots of cases. This is one of the simplest examples we'll see, but it's the kind of thing that shows up in lots of different kinds of applications. So we want to develop a way to integrate these kinds of integrals. So here's an idea. This is called trig substitution. I'm just going to proceed with it, right? This is not something you would just jump on and guess to do. I'm sure this method took some trial and error, or was stumbled onto in the course of other work. One thing that might clue us in is noticing that we have this 1 minus x squared. This is similar to some of the trig identities we've seen in the past. So let's try something. Let's try this substitution. X equals sine of theta, right? Again, this is like the reverse of the substitution rule, right? Typically, right, when we have the substitution rule, we're looking at something like f of g of x, g prime of x dx is going to be equal to f of u du, where u is equal to g of x, right? Usually we're given what's on the left and use this substitution so that we can write what's on the right here. In our case, we're actually starting with this and going in the other direction, right? And coming back to something that's going to look like this, right? Now, it's because in this case, what we're starting with is more complicated, and it turns out what this gives us is something that we can manage. So if this is the case, if x is equal to sine of theta, then we'll get that dx is equal to cosine of theta d theta. And this integral becomes, let's see what we'll get. We'll have 1 minus sine squared theta, right? Substituting where x was, I'm putting in sine of theta. And then where dx is, I'm getting cosine of theta d theta, okay? We still have to deal with the bounds, okay? Well, let's think through this. When x equals 1, sine theta is equal to 1. That will give us, if we can solve this for a value of theta, that can tell us the bound here. And when sine, and we need to find theta so that the sine of theta is equal to -1. Okay. Well, one of the restrictions or one of the issues we have when we do substitutions has to do with functions being one-to-one. We want them to be one-to-one so that in the substitution there's not complications where you're doubling up values. Well, the way we make theta a sine one-to-one is by restricting its domain, because as it is right now, there are an infinite number of solutions to this equation, sine of theta equals 1. Pi over 2 works, 5 pi over 2 works, 9 pi over 2 works. I'm just adding 2 pi and getting all of these answers. We're going to use the restriction, though, that theta has to be between negative pi over 2 and pi over 2. This is the typical restriction on sine to give it an inverse. And that way we can say, right, sine only has an inverse if we make a restriction, and this is the typical restriction. So the inverse of sine, the inverse sine of 1, then even though there's an infinite number of responses to this, an infinite number of thetas that give us a sine of 1, when we do the restriction, we restrict this to be pi over 2. And in the same case over here, the inverse sine of -1 is negative pi over 2. And so our bounds can be written this way, okay? All right, now let's deal with our integral. So I've got my bounds. I'm going to now use the trig identity, sine squared theta plus cosine squared theta equals 1, or cosine squared theta equals 1 minus sine squared theta. So I take 1 minus sine squared theta and make it become cosine squared theta, and I've still got cosine theta d theta. Okay. Carrying on. Now, let's do some more side work. The square root of cosine squared theta, right? If you take something and square it and take the square root, we want to say we just get it back, but that's not the case. We get the absolute value of it, right? If you take a number and square it and then take the positive square root, remember this symbol is not just the square root, it's the positive square root. You're taking the absolute value. For instance, if you take -3 and square it, you get 9. When you take the positive square root of 9, you get 3. So you've taken that negative number and made it positive. If you take this 3 squared, you get 9, and then square root, you get the same number back. So it does just what absolute value does. However, remember, we're dealing with the interval negative pi over 2 to pi over 2. On this interval, cosine is always positive, which means the absolute value does nothing. So as far as this interval is concerned, we do just get back cosine of theta. So we don't have to worry about that absolute value part. So I've got the cosine of theta coming from this radical, and then I've got cosine of theta here, so I've got cosine squared theta d theta. All right. Now we will use oh, sorry, I'm just looking at my notes trying to remember what I did here. I used a little trick here. Notice that cosine squared of theta is even over a symmetric interval. So we can take this, and instead of doing it from negative pi over 2 to pi over 2, we can do it from 0 to pi over 2. It's debatable whether or not that's helpful. I like it. Usually computing with zeros is easier, although in this case, I don't think it makes too much of a difference. And then I used this. This was one of our identities we looked at in a previous video. This is 1/2 1 plus cosine of 2 theta. Okay. So I'm substituting for cosine squared. This expression, I've got a 1/2 and a 2, so those two things are going to cancel each other out, or become a 1, I should say. And I've got 1 plus cosine of 2 theta, d theta. Now I can take my antiderivative. The antiderivative of 1 is just theta. The antiderivative of cosine of 2 theta is 1/2 sine of 2 theta. And I'm evaluating these from 0 to pi over 2. We'll come to this table in just a moment. And so I get theta pi over 2 plus 1/2 sine of 2 theta. So sine of 2 times pi over 2 is sine of pi, which is 0, plus, now I'm putting in 0 for theta, plus, oops, this should have been a minus. Doesn't matter since it's zeros. Sine of 0 is 0. So everything else after that pi over 2 becomes a 0. And we get the answer pi over 2, which is, of course, the same as the answer we had got using the familiar geometric formula. Okay? So obviously, this is not the best way to handle finding the area of a circle. You use the circle. We have a well-known formula that makes our lives a lot easier for doing that kind of thing. However, when we see integrals of this form, they're not always going to be circles, right? If I changed one of these, they can have different constants attached. We'll have some other stuff going on. So this is a simple example to show you the method, but we're going to see that in cases where we can't defer to the geometric formula, that we can still use this method in these more complicated instances. So what we have is several different situations where we're going to try this, this method out. And I've got a little table here showing these different situations. What you're going to look for when you get to an integral, so what I have on the left column is, in this expression column, is when you see something in your integral that looks like one of these, it tells you what substitution to make. So for instance, in the one we just did, we had 1 minus x squared. This was like this first expression, where a equals 1, right? Because then a squared minus x squared is 1 minus x squared. So we were using that form, and we used this substitution over this interval, and then we used this identity to get rid of the radical, right? You'll do a very similar thing when you see a squared plus x squared. So something like 4 plus, if we saw something like 4 plus x squared, this is of course 2 squared plus x squared. We would make the substitution x equals 2 tangent theta. Okay. If you saw something like x squared minus a squared, you use x equals a secant theta, right? So they're different identities, different substitutions, but it's going to be a very similar idea. You have a bunch of trig functions floating around. There'll be some cancellations, some things that combined, and then we end up typically in something like we had in the previous videos, where we have powers of sines and cosines, secants and tangents, and then we use some of those tricks. Like in this case, we ended up with a cosine squared, and we used this nice identity here. So that's it for this video. I'll do examples of the other ones. There'll be videos with examples of doing the other kind and more complicated versions of all of these. But this is just to introduce the idea. And this is a good table to get familiar with, because these sorts of forms show up quite often. Okay, thanks everybody. I will see you in the next one.